There we go. I'm trying something new with the camera. I took the fisheye off, so now it's narrow. I realized that when I started swinging the arm side to side, the infinity went pretty quickly to infinity into the small. And I added a microphone, which seems to pick up sound better. So hopefully, if you guys are using this, hopefully this will be a little bit more usable now as a resource. So anyway, sample average. How many keys do we have on average? 3.9. Michelle, thank you. 3.9 keys per person. I want to come back to that to talk about what exactly that means. I'm also going to swing the arm out so we can see what we're writing over there-ish. There we go, good. All right, how about median? What was our median number of keys, friends?
3.
3, exactly 3. Okay. And how about our modal number of keys? 2. Okay. So we got 3 keys, median, 2 keys mode, 3.9 keys per person. Grab one of those 3 measurements and explain it to me using other language than just the average is 3.9 keys per person. What does that mean? The median is 3 keys. What does that mean? The mode is 2 keys. What does that mean? Pick one of those and explain to me what it means to you in your mind. If you had to explain, for example, if you had to explain that the average number of keys per person in this room was 3.9 per person, how would you explain that? Go ahead, my friend. Tell me your name one more time. Tabitha, thank you. Go, my friend.
So if we collected all the keys between 32 people and distributed them evenly, each person would have 3.9 keys.
That's perfect. Love that. If we took all the keys, in other words, instead of you guys keeping your individual keys as you walked in this room, there was a little spittoon by the door, not full of spit, but you filled it with keys. You just dropped your keys into the little spittoon. So we had this big collection of keys. And then we dumped it onto the desk. And then made an equal-sized pile, 32 of them, correct? As you said, 32 equal-sized piles. Each one of those piles would have to have 3.9 keys in them, which would ensure the same total number of keys as we had in the room on whatever day that was, but now an equal number of keys for each person. Thank you. Perfect explanation. Absolutely perfect. What are some words that pop to your mind when you think of average? Share. Equal's a great one. Equal, share, love share.
Balance.
Share. Balance. All these words are fantastic. Balance, share, equal, perfect. Perfect, good. That's exactly what an average is. That's how I want you to think about an average. It can lead us astray sometimes, but it's also a fantastic way of describing use the word balance, the word share, the word equitable. Awesome, awesome. Grab one of the other ones, median or mode, and tell me. This is with Shelby. Go ahead.
Most frequently occurring number.
Absolutely. So of all now. Forgetting the average for a second, because the average actually ignores the individual amounts of keys and puts them all in one big pot. The mode actually looks at the raw values and says, oh look, 2 came up, looks like 8 times. That number showed up more than any other number of keys. So that's your mode. Perfect. Most frequently occurring. Beautiful, beautiful. Take a stab at median. What is median? How is median calculated, or what does it imply to you? When you can, Lucas, go for it.
Well, you have to line up all your data from smallest to biggest.
Good.
And then the center one, the one that's in the middle, is your median.
Love it. With that tone, especially, awesome. Totally awesome. Perfect. Absolutely perfect. Arrange it smallest to biggest, or if you choose biggest to smallest, although I think as human beings we like arranging from smallest to largest, and then find the actual geographic middle. So what you're learning here is the word typical, which is what center measures actually are going for, the typical data point. Typical is defined 3 or 4 or 5 different ways. Average, typical, means equal, means balanced, means shares. Median, typical, means the actual geographic middle. If you had 32 data points in a row, each one occupying one space, it finds the middle spaces, the actual middle. It ignores the actual sizes within. It just has 32 numbers in a row. So check this out. The numbers we have are 0 all the way up to 17, right? We put all those in order. If some of these 2s became 1s, the median would still be exactly where it is at 3. It wouldn't change a thing. So it looks only at position of the data points, not the values of the data points. And then mode is simply a measure of frequency, which one pops up the most. So each one of those is typical, but typical in different ways. And we'll see today why we like some of them in certain situations and we like others in other situations. Sometimes I don't think we should use some, but it's not always obvious. I think everybody's talked about these before in their lives, but maybe you haven't taken a look at why we should or shouldn't use them. I'd like to start with that next, if that's okay. Any questions? Those explanations are perfect. All three of them are absolutely perfect.
Median doesn't really seem like it does anything. Really, like.
I mean, when you say it doesn't do it, no, hang on. When you say it doesn't do anything, what do you mean by that, Chris?
It doesn't give like a reliable number, a reliable
Hold that thought.
average. Like,
I disagree, but you don't see why yet. I disagree, and I love that. Yeah, Chris is saying the median doesn't give a reliable average. Well, that's actually arguable because the average gives an average, the median gives a median. So I mean, technically speaking, it's like Slayer doesn't do a good job of doing mating.
Yeah.
Because Slayer and mating.
Yeah.
But to say that they're both not good at the metal band is a different story.
Yeah.
So to say that these guys maybe aren't or are interchangeable in their usage, let's address that next. Great point. Great point. I love it. So let's go back to here. Let me adjust the screen, the camera again, so the camera grabs it. I'm going to have these graphs posted for you guys this afternoon, so you don't have to worry about drawing them or writing them down or anything like that. Let's slide this in a little bit more, maybe. Oh, that's good. High tech. Box of staples holding the leg up. I like it better already, actually, because not going to the crazy fisheye wide angle, the little robot shadow doesn't appear in the picture anymore. So that makes me a little bit happier. So unfortunately, shooting in high def now, the only way I can get it narrow is to shoot in high def. And I just dumped the card from the last class to make room for this one. It was like 7 or 8 gigs. I'll try to stay on top of uploading stuff for you guys, so it's up within 48 hours. I just, with that kind of file size, having to convert it to AVI file, then get it to YouTube, a little bit of editing, I'll just keep it going as quickly as I can. It might take a little bit longer to get stuff uploaded now. Anyway, what am I looking at right here?
Bad cholesterol.
Good, men's cholesterol, good, LDL. Does that have to go to the bad cholesterol? That's the bad, low density lipids, bad cholesterol. You said men's cholesterol, right, Chris? Love that. How many men? How many men in the sample? Go ahead, be brave, my friends.
100.
Tammy says 100. I'm tempted to agree for a couple reasons. Number one, I was kind of nice to you by putting n equals 100 up there. But also, you can get a ballpark, can't you? Tammy looked at the n equals 100 and said it's 100. Absolutely. You can also get a ballpark. Look at the bars. Look at that vertical axis. 0, 5, 10, 15. What's that vertical axis showing you over there, friends?
How many people?
Good. That's your frequency. That's how many people. What's on the horizontal axis down there?
The measurement of
Yeah.
Exactly. Measurement of their LDL. If I remember correctly, and I probably don't because I'm me, I think it's something like milligrams per deciliter. I think. Is that correct, Amy? Good. Milligrams per deciliter, so it's a density. Milligrams per deciliter. So anyway, this is not raw data. This is group data. This is now given to you not in a distribution. What's this fancy graph called again? Perfect. Awesome. Histogram. It's technically not a histogram. You can call it a bar chart if you want to. It's quantitative data. So you've got numerical measurements across the bottom, below 3.25, 3.25 to 3.7, 3.75 to 4.25, and so forth. But we don't have the raw data anymore. However, if I asked you to find one of the 3 measures of center for this graph, could you do it? At least when I say this, at least ish. Could you ish give me one of those 3 measures of center? Go ahead. Let me hear some ideas. Pick one measure, tell me what it is, and tell me how you found it. Give me one measure of center. Corey, what do you think?
Mode.
Mode. Go for it, Corey. What is it?
4.75 to 5.25.
Corey's vote is the mode is 4.75 to 5.25. Tell me why you think it is.
Largest bar.
Largest bar. What's the definition of a mode, as Shelby told us before?
The mostest.
The mostest. Excellent. From now on, that will be the definition of mode. It's the mostest. And that is the mostest bar. Thank you, friend. It's on video. It's even better. The mostest bar. Right. And if you want to, you can go ahead and just call that whole bar 5. Because it's the middle of 4.75 to 5.25. What's the problem? What's the problem with data grouped in these histograms versus raw data?
You lose the actual amount of what that measurement truly was.
You lose that precision, Mike Hess. Exactly. You lose the precision. So you know that there are how many people in that group, 4.75 to 5.25?
About 32.
Like 32, 33, somewhere in there, right? There's like 32, but the problem is you don't know what each of those 32 LDL levels are. So you know they're between 4.75 and 5.25. They could all be 4.75, which is unlikely. They could all be 5.25, which is also unlikely. It's more likely that they're spread evenly throughout the interval. So calling them all 5 is totally fine. You'll see why momentarily when we go back to the key data. I promise you that. Good. So mode, mostest, about 5. Grab another one, mean or median. Your choice. Your choice. Think about the words you guys used for average before. I heard share, I heard equitable, equal, and I also heard
Balance.
balance. Can we use that? Can we use balance to help us find the average on this one? Imagine that as a scale, and the weights are the heights of the bars placed onto the scale. So the higher the bar, the heavier the weight. Higher the bar, the heavier the weight. Because each guy, each person counts once, but this stack is 32 times as heavy as this stack, because that stack only one high. Does that make sense? It's about 5 or 6 times as much as that stack. So imagine that as a scale. Where would I have to put the fulcrum of that scale to balance it? You tell me where to stop. I'll start over here. Tell me where to stop to balance the tray. Stop in here?
Around that.
Ish, yeah, ish. It's kind of matching up with what Corey just said about the mode, huh?
Yeah.
I'm tempted to agree. You've got just about the same amount of weight over here as you do over here. So I'm thinking the average is also somewhere in the neighborhood of 5. Love it, love it. So you got a 5 for an average, you got a 5 for a mode. How about a median? What do you guys think?
It's the one that happens the most.
That's the mode.
Well, that's the most.
That's the mode.
The one in the middle.
You described the median perfectly, Lucas.
No, I know.
You
Earlier.
did. You're the man. No. Can we use your method on this graph?
We don't know the exact number.
don't have
We
the right-
don't. But can we use Lucas's method? Because remember, the median doesn't need the exact values of each data point. It just needs the values in
Middle.
the middle, which means we have to have them in order.
So it's the smack of the very.
Exactly. We can do what we did with the keys with this, I think. Remember what we did with the keys? We lined up the keys from whatever it was, 0 to 17, and we started chopping. Chop highest, chop lowest. Chop next highest, chop next lowest. I think we do that with this.
So then it'd be 5 also.
I think so. I figure, Raphael, because if I chop the lowest
Okay.
with the highest, they're gone.
Right.
Let's chop, what's this? This is like 7.
7.
Chop those 7.
7.
This is like 5, and then chop 2 more. Excuse me, chop 5 and then, yeah, 5, or this is 4, and then 3 more, so that's 7. We got a couple left over here. Let's chop them with those couple up there.
Okay.
So now we're down to this bar, and this bar, right?
Yeah.
So let's just chop all of this bar, which would be like 25 left, right? And then chop, what is this, 21? Which means now we have 4 left to unbalance. Let's take these 4 out. So now everything's gone except this bar in the middle, which means whatever we chop now, we're within that bar, aren't we?
Yeah.
So that means the median is basically going to be the same as the mode, is basically going to be the same as the average.
Yeah.
So essentially, the mean, median, and mode are all going to be the same. And what's nice about that is, with data that's shaped like this, that's always going to be roughly the same. What kind of words would you use to describe, if this were a graph, say from Math 111, what kind of words would you use to describe this? Or a graph in psychology class, for that matter. Bell curve, love that. Who said that? Bell curve, that was awesome. Tell me your name. Kelsey, thank you. Bell curve, beautiful, bell curve.
Symmetrical.
Symmetric's another great, was that you, Athena? Symmetric, yes, that's a more general, bell curves are symmetric. But symmetric curves can include more than just bell curves. So yeah, how many modes? How many modes does this data have? Just one, just that one bar in the middle. So I'm going to use 2 words to describe this. Symmetric, unimodal. Symmetric, unimodal. And if you have this kind of data, it doesn't matter what measure you use, because they're all essentially the same value. And like I said, friends, I'll have this posted later. If you don't want to scratch stuff down in class, you just got to kind of take it in and understand. Make notes. I'm not saying don't take notes, but don't feel the need to slavishly write that everything on the screens. So yeah, when you've got bell curves, when you've got just purely symmetric data that only has one mode, go ahead and use anything you want as far as center goes, because they're all the same anyway. They're all the same anyway. The thing is, you don't always have this. Chris, we're getting to answer your question. We're going to answer you, because Chris's question is still on the back burner as far as what's the point of the median? What's the point of the median? Right here, there really is no point. If the average does the same as the median, then why not just talk about the average? Because there are sometimes the average might paint a picture that isn't quite the picture we should paint necessarily. But when you've got bell curve data, when you've got symmetric data with single modes, or arguably single modes, yeah, take your choice. They're all about the same. Ours, it's hard to see if ours are same-ish or not, which is, we'll take a look at ours graphically later. I'll have you guys describe our data graphically. So this is, like I said, symmetric unimodal. Here's some data. I was in the middle of updating this today and I ran out of time. So we've got it from 2009. I apologize, it's a little bit old. But it's sale value, sale prices on houses in Bend. So take a look, try to make peace with what you're looking at first. There's a lot up there. There's a lot up there. But this is the internet, friends. This stuff just comes flying at you, facts and figures and graphs and charts and data, and you have to kind of process it. So this is kind of like a little mini version of that. First of all, sale listings as a function of sale prices. So basically, how many houses are selling at certain prices? Okay, how many houses are in this sample? Ish. I wasn't nice enough to you this time. I didn't give you an n equals something up top. So how many houses do you think are representative in that sample? What do you think? About 600? I like that vote. Wait. Got too much good in me. About 600? Is that okay? We don't have to know that because I'm not going to make you compute anything with any precision off of this curve. Mostly because I've given you all the values down there. So we've got a few hundred, don't we? The highest bar up there at 2 is showing 200. We've got a couple bars at 125. So we've got a few hundred houses represented up in here. Beautiful, beautiful, beautiful. The horizontal axis is a little bit hard to swallow only because I wanted to truncate it down and make the prices out of $100,000 because the numbers were getting too big and they were clogging the horizontal axis. So basically this 1 should be here. That 1.5 there, that 2 there, and so forth. So it's cutoffs. This is the number of houses between $0 and $100,000. Number of houses between 100,000 and 150, 150 and 2, and so forth and so on. So hopefully that makes a little more sense. Now, would you describe that data as symmetric? The word symmetric popped up before. What does the word symmetric mean mathematically or artistically? Let's back up to the symmetric curve for a second. What does symmetric mean as far as mathematics goes? Corey's going like this, and I like this very much. So, what do you mean verbally with this?
Identical on one side.
Excellent. If I could do it, I would. If I could fold this part of the graph over, it would essentially lay on this side of the graph. So left and right, symmetry about a vertical axis. Very nice, very nice. Would you describe this curve as that?
No.
I don't think so. I mean, no matter where you decide to put a vertical line, it's not going to mirror itself on one side or the other. It's got a bellish-shaped hump here, but then it tails off.
It's weighted to one side.
Say that again.
It's weighted to one side.
Excellent, Thena, excellent. It's weighted to one side. We've got a special word for that called skewed in statistics. Skewed, only because weighted is used for something else, which we're going to talk about today as well. But this one was even more weighted originally. See, I got this word without outliers and with outliers. I know we haven't defined that term yet, but I think you have an idea of what it means. Outliers are unusual data points. There were a lot more prices than what are shown right here. These are all the non-outlier house values, so $800,000, $600,000, $400,000. There were a few that were in the millions, and there was at least one that was like 14.5 million or something along those lines. And the graph kept going. There was bumps out here, bumps out here, bump out there in the bathroom. It kept going. It kept going. It kept going. But I wanted to prove a point. So what I did, because of what Athena just said, because of the graph being loaded to one side, look at the measures of center with and without the outliers. This is finally going to answer Chris's question a few minutes later. Cassie, what are you thinking?
Oh, I just noticed that the median and mode on both were the same.
The median and the mode on both are the same. Let's talk about why. If you include these very expensive houses out here on the right side, why wouldn't the mode change? For example, the mode. The mode was $175,000 with just these data points, and it was also $175,000 if we include these plus all these other ones that are down there.
Because
Pretty far.
Those do not happen frequently. That's very infrequent that those prices would be in that.
The definition of an outlier.
Yeah.
Unusual data points. Unusual is kind of the opposite of frequent. So since we didn't have, say, a spike of 556 houses that are all $14.5 million, which would change the mode, but then we'd also have to reclassify our definition of what an outlier is. But we didn't have that. They didn't happen frequently enough. Raphael said it perfectly. They didn't happen frequently enough to affect the modes at all. Perfect, my friend, perfect. How about the median? Why isn't the median affected?
Because the median.
It's easy to say median, I do it all the time too.
Is still going to be the center point, no matter what.
The geographic center.
Right.
But doesn't it have to move if we're going to add more houses? This is the one that's a little bit tricky. What you're saying is correct statistically, Raphael. Perfectly correct statistically.
But I mean, if you had like 17 of those that were the same number, then your median would shift.
So Raphael's point is, suppose we had, I'm going to go even more, I'm going to exaggerate even more. Suppose we had like 200 outliers that were all down there in the tail. Now, in order to find the median, like we did on the last graph, we had to chop. Chop, 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 right? And once you get done chopping, the median ends up being right around $300,000. So it's going to be in this bar right here. Raphael's point is, when we add a few outliers in, yes, clearly there are now more data points to chop, but we might move, say, from this position of the bar to this position of the bar. We're not adding so many that it's going to remove us from this bar and put us into a significantly different bar. Perfectly said again. That's 100% correct. If there were, say, for example, 50% more data points down there, number one, it would change the median, and number two, I don't think I'd be calling them outliers anymore. Right. I'd be saying this is a very expensive market.
It's much more frequent.
It's much more frequent, which doesn't make them atypical. We're looking for atypical with outliers, not typical. Awesome. Why does the average change? The average does change. That was your sample average without those goofy data points, $300,000. With the very expensive houses, it was $400,000. And this happens all the time in real estate. People talk about their house value going up because somebody builds a big house in the neighborhood. Lucas?
Well, if you add the outliers, it's going to be more expensive because you're taking all of the amounts, putting them together, and dividing them by how many.
So this number right here grows.
Yeah.
But so does this one.
Right.
They both grow, don't they? Because we're adding more houses into the mix. So as we saw before, there's about 600 houses in this sample here. So that would be 600 for the original average. If suppose we add 25 more outliers that are very expensive, well now this is 625. So you're dividing by a bigger number, which should make the overall thing smaller. But what Lucas just said is correct. This is getting much bigger than just that 25 over 600. So you're getting a disproportionate amount of growth in the numerator. And this is the problem with data that is skewed like this. I added one more measure right in here. It's called a trimmed mean. We'll teach you how to do all this in Excel in your first take-home exam. I got a great question with my chicken and egg production in the 4 chickens we have at home. And it teaches you how to kind of get all this stuff in Excel, which is the way you want to do this in general. It's much easier than doing it by hand. A trimmed mean means you take the entire data set, outliers and non-outliers, but you lop off a certain percentage at the top and the bottom. So a 5% trim means you dump off the cheapest 5% of houses and the most expensive 5%, and you re-average the middle 90% of houses. And notice the trim mean went down from the 100% mean, but it's not down as low as the outlier-less mean. Which means removing the high outliers with the low-valued houses did take away some of that inflation in the average, but not as much as taking out the truly unusual values would have done. But it's a way of mitigating. It's a way of mitigating this. But so Chris, here's the point. The point is, if you actually do have data, and the more skewed, the worse this gets. The more skewed, the worse this gets. When it's skewed, your average is going to chase the tail of the graph. So this is called, believe it or not, this is called right skewed data. It's called right skewed. Even though the graph is leaning to the left, it's called right skewed because the average is heads to the right. For some reason, I don't know why, statisticians have named skew based on where the average goes. So I don't really worry about left versus right. I care about the fact that if it's skewed or not. Since it's skewed, the average is going to head towards those extreme values. And that's a bit of a problem. You might make decisions based on skewed data, like I can or I can't afford to live in a certain neighborhood, based on the fact that 1 or 2 houses on average might drive the prices up or down. Whereas a median would be a much more representative view of what's going on in that case. You buy that, Chris?
Yeah.
Ish?
Yeah.
Ish. Yeah. When you have highly skewed data, averages can mislead you.
Yeah.
The average is going to, I'm not saying there isn't an average of the data, because there is. I'm saying that it might not be the best thing to look at for this particular data set. Sometimes it is bell-shaped data. I'm totally down with that. And we get bell shapes a lot. We get lots and lots of bell shapes in statistics. But sometimes you don't. Sometimes you get stuff that looks like this. So that's when you take a step back and say, okay, I like the median now. Is that fair? Yeah. So don't worry about left versus right skew. And also, one of the things to get used to in this class is the quantification of how skewed is skewed. Like, how skewed. So basically, here's the baseline is a perfect bell curve. A perfect bell curve has 0 skew. As soon as it starts leaning to one side or the other, it starts becoming skewed. But quantifying that gets tricky. So we'll attack that soon. I'm thinking like next week, early next week, we'll attack how to quantify skew and how skewed something is numerically. But right now, looking at that, we can't do Corey's fold trick to figure out that it's not, that it isn't symmetric. So therefore, it is skewed. So just be careful using averages on skewed data. Cool so far?
Yeah.
Yeah? Okay, good. This next one's some fun data. This is about 4 years ago again. Some really weird crap happened during one exam that I gave in my Math 95 class. And this was the result of the exam. This is